In this presentation, I will discuss the physical laws that explain how objects fall under the force of gravity when friction is insignificant. I'm going to discuss the effect of mass on a falling body and how the velocity of an object changes when it is in the state of free fall. For the purpose of this discussion, free fall describes the motion of an object falling due to the force of gravity where the force of friction is negligible. Something is negligible when it is so insignificant that it can be ignored. The video on the left shows a man leaving his third-floor apartment in a very unusual way. Since the force of the tree on the man is not negligible, he, of course, cannot be said to be in free fall. Now look to the right. When a leaf falls off a tree, it also does not exhibit free fall. Because it has a large surface area and a small mass, air friction has a significant effect on how the leaf falls. Even though air friction is present when all objects fall at moderate speeds, and for most objects, the force of friction has a very small effect on the motion of a freely falling body. So in cases where air friction has only a small effect, what factors, if any, determine the motion of a falling object? Before the Italian scientist Galileo proved otherwise, most people were certain that heavy bodies would always reach the ground quicker than lighter ones. In his very famous experiment, Galileo dropped various sized masses off the Leaning Tower of Pisa and proved that mass had no effect on how an object fell. As long as friction was negligible or insignificant, heavier objects don't fall any differently than lighter ones. For most people, it's not obvious why an object with a greater mass would fall exactly the same as an object with a smaller mass. After all, an object with a greater mass has a greater force of gravity on it. In Newton's second law, we see that there are actually two factors that explain how an object accelerates in the presence of a net force. His second law of motion equation, shown here, tells us that mass also has an effect on the acceleration of a body. To understand how mass affects acceleration, imagine that the four boxes you see here were resting on a smooth, frozen pond. If you applied the same force on all four boxes, you wouldn't expect every box to have the same acceleration. Box C with the least mass would have the greatest acceleration, and block D would be accelerated the least. The more mass an object has, the more difficult it is to accelerate. A box with 10 times the mass is 10 times more difficult to accelerate. By the way, an object's resistance to a change in motion brought about by a force is called inertia. Don't worry about this now. We will discuss this concept in greater detail later on this year. Now imagine we drop C and D from the top of a building. Since block D has 10 times the weight, why wouldn't it fall with 10 times the acceleration? This is because the acceleration of any object in free fall depends on the force and the mass. Block D has 10 times the force of gravity on it, but it also has 10 times the mass. With 10 times the mass, it's 10 times more difficult to accelerate. The two effects cancel each other out. Here is a slow-motion video of a 200-gram mass drop from the same height as a 500-gram mass. Notice that at every moment, each weight has the same height above the ground. Despite having 2.5 times less weight, the 200-gram mass falls exactly the same way as the 500-gram mass. A moment-to-moment analysis of an object moving up under the force of gravity reveals that it moves with a constant negative acceleration. After it reaches the peak, it moves down with a constant positive acceleration. Furthermore, the time it takes for the object to reach the peak is equal to the time it takes to return to its initial position. On the moon, which has virtually no atmosphere, a feather falls exactly the same way as a hammer.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? It proves that Mr. Galileo was correct in his findings.
When you plot the displacement of a falling body as a function of time, you get a plot whose slope smoothly increases. Since the slope of the d versus t plot is equal to the velocity, this tells us that the velocity is increasing at a constant rate. A constant increase of velocity occurs when an object has a constant acceleration. This means that it gains the same amount of velocity in each second that it is falling. All objects falling near the surface of the Earth accelerate at a constant rate of negative 9.8 meters per second squared. Remember, that's neglecting air resistance. In this presentation, you learned that when air friction is insignificant, all masses accelerate at a constant rate of negative 9.8 meters per second squared. An object always has a velocity of 0 meters per second when it reaches the peak, and the time it takes for an object to reach its peak is equal to the time it takes the object to return it to its initial position.